right, welcome to quantum field theory. Today we're going to do one of the more exciting things in this course. We're going to take a field and we're going to quantize it and solve it. It's going to be more or less the only occasion in this course where we'll be so successful. But it is such a beautiful and exquisitely powerful example that we'll use it throughout our entire course. So the topic, as I introduced in the last lecture, the topic we're going to move on to now is relativistic quantum field theory as opposed to just relativistic classical field theory. Now, relativistic classical field theory is a lovely topic, very beautiful. We can say very much, but it's not quantum theory. And if we want to do quantum field theory, we're going to need somehow to find some quantum systems that we think we can call quantum fields. And just to remind you, this task of finding quantum systems that behave in a way what we like, this task is not really a well-posed problem, this task of quantization. So if you think of the space of this not properly defined space of quantum theories consisting of Hilbert spaces and Hamiltonians, this not yet precisely defined space here is not what we typically perceive with our everyday experiments. Instead, what we typically perceive of the universe only allows us to access low energy, large scales, and typically our experiments are subjected to large amounts of decoherence. In this limit where you take a quantum theory and you study only its low energy, large scale sector subject to decoherence, then we know, basically from experience, that a good effective model for this particular limit is classical theories with a Poisson bracket, some Hamiltonian, and some phase space, which I didn't write down here. Here's phase space M. So the space of classical theories governed by the data of a phase space, a Poisson bracket, and a Hamiltonian H arises a fantastic effective theory for quantum theories at low energy, large scales, and in the presence of decoherence. That's just the way it is. That's how we discovered physics. It has, however, the awkward feature that if we want to discover what the right quantum theory is that led to this classical theory, suppose you have a classical theory here in the space of all classical theories, what's the quantum theory that led to that? Right? Well, you've got to undo these limits to find what it is that is the quantum theory that led to this particular classical theory. Somehow we want to go backwards, right? And inevitably, this limit here, governed by this effective model, we've lost some information. It's just inevitable. If we can only access low energy, large scale excitations in the presence of large amounts of decoherence, then there are degrees of freedom we can't access, and therefore we don't know how they're described. So that there must be more than one quantum theory that can have the same classical limit. This is indeed the case. Turns out there are indeed more than one quantum theory that have the same classical effective. There's more than one quantum theory with the same effective classical description. So there might be one here, there might be one here. In the limit of large scales, what happens at small scales obviously doesn't change the effective dynamics that we give to the theory at large scales. So there's more than one quantum theory that can have the same effective large-scale classical limit. So the very idea of asking for an quantization scheme, some canonical scheme, which given a classical theory would give you the right quantum theory, is obviously not well posed as a problem. This is the way of the world. This is what we're presented with in physics. We always get to see the results of bad experiments, and we have to work out what it is that's driving everything behind the scenes. So quantization, when you see this word, you must always translate it to educated guess. Otherwise, you can spend a long time in your life trying to discover canonical, correct, mathematically precisely defined maps that do this quantization procedure. But I claim that such a thing doesn't make sense. Now, we've gotten pretty good at doing these educated guesses. So over the past 50 years, we've explored lots of quantum theories, taken these limits, and then we've got a fairly good understanding of what it is the right quantum theory corresponding to a given classical theory. And it turns out as long as your classical theory is quadratic, meaning that the canonical variables appear only at most order 2 in your Hamiltonian, then all these quantization schemes that people have cooked up, they all more or less agree, and the problem is basically well posed, and you can write down a reasonable quantum theory for a classical theory. So in the quadratic case, I'll just say solved. There's presumably some mysteries left in the quadratic case, but most of the basic stuff is now settled down. So our particular way of guessing that we're going to adopt in this course is called canonical quantization. This is a pretty nice scheme for guessing quantum theories. It works out in the case of quadratic theories. In the case of nonlinear or interacting theories, it has problems, but so does every other quantization scheme. So to get into this, I don't want to talk about fields at all. I want to talk about discrete systems to begin with, just to remind you how the canonical quantization prescription works. We're going to start out with n degrees of freedom, n classical degrees of freedom. And we're going to guess, and these classical degrees of freedom, we're going to label, they have canonical variables qj, pj, so the position of momentum variables are qj, pj. We have a Poisson bracket. Do I do p? No, q. So the Poisson bracket between these pairs is just the standard one, delta, Kronecker delta, and Hamiltonian function on phase space. Well, I told you it only really works in the quadratic case. We're going to stick to the quadratic case. That's interesting enough by itself. So we're going to suppose that our system of classical degrees of freedom is governed by this particular classical Hamiltonian. Let's suppose we have n degrees of freedom with that classical Hamiltonian. What is this? It's just a bunch of harmonic oscillators interacting according to some spring-like potential. Now, the question is, what's the right quantum system that has this system as its classical limit? Well, there's not a unique answer. I can think of two absolutely, completely different quantum systems that have exactly that Hamiltonian as their effective classical limit. One is comprised of a bunch of quantum spins, and the other is a bunch of quantum harmonic oscillators. I won't tell you about the quantum spin version. I'll just tell you about the harmonic oscillator version today. And that's what we're going to call a canonical quantization. So even though there's multiple quantum theories that have this as their classical limit description, we're going to choose one because we believe in the almighty power of the harmonic oscillator and choose that as the right one. So how does it work? Well, we promote Qj, Pj to observables on a Hilbert space. That means self-adjoint operators. First step in quantizing something, right? Functions on phase space become operators. The Poisson bracket, oops. What does that become? Well, we know that we got to take our observables and impose some commutation relations on them. And you've got to add in that I. Important. In fact, without the I, it doesn't work because these couldn't be self-adjoint then. And the Hamiltonian, what do we do with that? Well, this is the guessiest bit of it all, I suppose. There's multiple ways you can stick operators in place of these variables here. Oh, I'm sorry, I'm just going to change these to q's just to be consistent. Little q's. There's multiple ways to build self-adjoint operators on Hilbert space from this classical guy. Right, it doesn't look like it at this stage, but because of the fact that these operators no longer commute with each other, it's possible to imagine all kinds of corresponding self-adjoint operators that you could write down here. In fact, this example has been chosen to not exhibit that difficulty. But if you had a worse example, would have a classical Hamiltonian that looks something like XQP, sorry. So the classical Hamiltonian is a perfectly well-defined function on phase space. But the corresponding quantum Hamiltonian, if you put hats on Q and P, well, now you are in trouble, right? Because Q times P, that's not Hermitian. It's not self-adjoint as an operator. So you've got to do something, right? Do you have a half QP plus PQ? You could do that if you want, I suppose. Or do you have square root Q, P square root Q? What's the correct quantization? Well, the correct quantization is the one that gives you the right answer. So we will choose through lots of experience, we have a recipe, and that is we try and avoid writing down Hamiltonians like that. So that's a great way to avoid this problem. You just don't let yourself encounter it. And luckily, nature's been very kind to us, and we don't often encounter Hamiltonians like this. Yeah, they do come, they do turn up. Sadly, it's not all easy. But for most of this course, we won't need to worry about such nasty things. All right, here we have imposed canonical quantization recipe, and it's as simple as put the hats on. That's how you quantize. You put the hats on, change Poisson brackets to commutators, and then you are done. So quantizing fields will just be a slightly more advanced version of exactly this procedure. The only subtlety being, instead of a sort of discrete number of degrees of freedom, we now have an infinite number of degrees of freedom. So this Hamiltonian here, actually, before I move on, this is a very interesting Hamiltonian. So it's a generator of scale transformations for a single classical variable. And it turns out that if you could cook up the right quantization scheme for this Hamiltonian, there's this conjecture of Polya and Hilbert, and more recently Keating and Berry, that if you could cook up the right quantization of this Hamiltonian, you would in fact prove the Riemann-Zeta hypothesis. So there's reasons to think that this Hamiltonian here, the simplest of all weird Hamiltonians, may have in it a trace of something somewhat deeper in maths. So quantization it turns out is linked to all kinds of things in mathematics, and perhaps even the Riemann-Zeta hypothesis, although I don't advise that as a research direction. All right. So much experience tells us that this works in the case of quadratic systems. In the case of higher order interactions, suppose the Hamiltonian had a fourth order interaction here, care must be exercised. Now, what does works mean? In the case of fields, it means works means that we can write down a representation of the Poincare group. In the next two lectures, we're going to apply exactly this scheme, in the case of fields, to write down a unitary representation of the Poincare group. We will write down a Hamiltonian, which gives us the time translations. We'll work out all the other conserved charges from Noether's theorem. We'll write down quantum versions of those conserved charges. They'll obey the right algebra, and we will have hence a representation of the Poincare group. So we will have legitimately quantized the field. Remember what I said in lecture 1, that quantization of a field means giving you a representation of the Poincare group. Good. But before we quite get to fields, I want to solve this Hamiltonian here, because there's much to be learned from this example in field theory. So what we'll see is that everything you can do in these discrete settings here has just a complete natural analog in the case of quantum fields, and that's the motivation for all the manipulations we do. So if you don't know how to solve that, then when you try and solve a quantum field, you'll be like, whoa, why are you doing this? The motivation for all the manipulations in quantum field theory come from the manipulations with this much simpler example here. So I want to spend a little bit of time just reminding you how to solve this model here. I know you've all solved the harmonic oscillator, and I'm sure I'll see some of you in exams in the coming years, and you know I'm going to ask you how to solve the harmonic oscillator. So it is worth taking the time to just remember how to solve the quantum harmonic oscillator, which this is at its heart. Because all of the manipulations we're going to do with fields would just be direct analogy, the direct analogues of what we're about to do now. Oh, I didn't say that Q was symmetric. Q is for us an n by n symmetric matrix. That's a slight, that's basically no restriction at all in this case. You can always make Q effectively symmetric. So since Q is symmetric, we know that there exists an orthogonal matrix O which diagonalizes Q. We know that. So we know we can diagonalize with an orthogonal matrix this symmetric matrix Q. Furthermore, this diagonal matrix, we're going to allow it to have a very specific form. We're going to assume these are positive eigenvalues. So not only is it symmetric, but it's also positive. You might wonder, what kind of a restriction is that? This is no loss in generality because we can shift the zero of energy of our Hamiltonian to make this positive. We'll see that I'm not going to bother with explaining that, I think. Good. So taking this observation here really tells us how to diagonalize our operator. And the way we do it is we introduce new quantum variables, exploiting the fact that this n by n matrix here diagonalizes our Hamiltonian. So we introduce these new operators Q, J hat. What are they? They're just the sums of old operators weighted according to this orthogonal matrix O. Well, that's Q's, but what about P's? Same story. Now, the reason we have to rotate the P's as well, although you might not think that you have to, is because we have to maintain the canonical commutation relations. So it's an exercise to check that indeed the canonical commutation relations are preserved by this change of quantum variables. It's enormously important. I mean, you can make changes of variables that don't respect the canonical commutation relations, but then you won't know how to solve the model later. So it's This is already like most of the solution, actually. Because if you substitute in these new variables into the Hamiltonian, you'll see that it acquires a very nice form indeed. Oops, using Q's. What I've done in going from our original Hamiltonian written here to there. So original Hamiltonian is here, expressed in terms of QJs, but I've expressed this now in terms of Q prime J's over there. And to get it in terms of Q prime J's, you have to use the fact that this matrix here is orthogonal, so that the inverse transformation is just the transpose. And that's why there's T's up in here. So far, so good. But if you look at this, what's OT transpose the JL's entry? Well, that's just the same as the LJth entry of the O. And then, well, now you're multiplying O by Q, and then you're multiplying Q by OT. And if you look up there, you see that that's a diagonal matrix. So we get a nice little delta function. The exact same argument applies to this momentum operator here. So you can just change P to P prime. Same argument as what I'm doing over here in more detail. And we end up with that expression here for the Hamiltonian, the quantum Hamiltonian. Now we are basically done. If you know how to quantize a harmonic oscillator, then you see that you're looking at n independent harmonic oscillators here. And if you don't remember, I'm going to write out the answer. So if you have a harmonic oscillator, remember you can diagonalize it in a variety of ways. Either you can replace P by the differential operator and then you solve a differential equation, or you can introduce ladder operators and express your Hamiltonian in terms of A's and A daggers. We'll take that path. And define the annihilation operators AL and AL dagger accordingly, just by taking the dagger. And then in terms of these operators, it's a very good exercise to do the tedious substitution of A's in terms of Q's. Of Q's in terms of A's and A daggers. It's very much worthwhile doing that, substituting it in the Hamiltonian. And then I've done it in my notes here, but I'm not going to write it up because I think this is a good exercise for you. You end up with the following expression. Should be very familiar to you. And that is none other than the harmonic oscillator for n independent oscillators with frequency omega L. This is an L. Not bad, right? So we've diagonalized this interacting system of n harmonic oscillators, and with one substitution and some derivations, ended up with this diagonal expression here. And we all know the eigenvalues for the harmonic oscillator, right? Half omega L times integers plus halves. So that's it. Now what we're going to do is the continuous version of all of this. There's a direct analogy between these somewhat elementary steps here and the much more sophisticated quantum field steps. Put that up here and keep that for the moment. Yeah, let's canonically quantize a field theory. So the canonical variables Q and P are now replaced by phi and pi, the field position variable and its conjugate momentum density. And these get quantized, not entirely surprisingly, into Q hat x and pi hat x. Our first guess at a quantum field theory is that we should put hats on things. So far, so good. Now, what about the Poisson bracket between these fields? Oops, that's not a quantum field. Well, the Poisson bracket between two classical fields is a delta function. And this, by this Poisson bracket here, I mean the equal time Poisson bracket. So this is equal time. It's a D3, the delta, Dirac delta function of the spatial coordinates. What should it be over here? How do we quantize that? Well, we know that you've got to replace commutators, Poisson brackets with commutators. So evidently, the correct way to quantize the field is to put hats on the fields and commutators instead of Poisson brackets. make you a little nervous, an expression like this. We've got the commutator of two self-adjoint operators as something that's not even a function. So care must be exercised interpreting this rigorously. And finally, well, we have a Hamiltonian, don't we? In the last lecture, we talked about a particular field theory, classical field theory. It's called the Klein-Gordon field. And it has a Hamiltonian. We worked it out. It's a half d3x pi squared x plus grad phi x squared plus a half, and I've got an m squared here. So that's the classical Klein-Gordon Hamiltonian, and you know how to quantize that now. Evidently, the only correct answer is to put hats on it. Okay, yeah. That's how you do it. Now I claim, if you look at the solution that I wrote down in the previous case of the discrete collection of harmonic oscillators, and you were willing to work by analogy enough, you already know how to solve this model. So pi squared x looks very much like pj squared. The only thing that's changed is that subscript j has now changed to an x. Grad phi x, it takes a little bit of sort of squinting, but if you replace grad phi with a discrete derivative, then that looks very much like the q. It's a quadratic expression involving little q's. Maybe it's like the q matrix. Maybe it's even symmetric. And half m squared phi squared, well, that's just easy, right? That's just q squared. Wherever you see an x, so the discrete label j goes to the continuous label x. And instead of writing q subscript x, which I hate, I'm writing phi x. All we have to do, therefore, to solve this quantum Hamiltonian here, if you're willing to work by analogy, is to work out like what's the analog of the Q matrix, what's the analog of diagonalizing the Q matrix, and is that all there is to it? Maybe it is as simple as that. And in some sense, we're going to show that it is as simple as all that. There's no fancy stuff that's going to take place. We're going to do exactly the same manipulations as I did for the discrete case, replacing sums with integrals. Nothing more. No more sophisticated steps. And that will allow us to diagonalize exactly that operator here. We'll be able to write down all its eigenvalues and its eigenvectors. But by the end of today, we won't yet be convinced that it's a quantum field theory, because to be a quantum field theory, it has to give a relativistic quantum field theory, it has to give a representation of the Poincare group. And just knowing the Hamiltonian, that's not enough. That just tells you a one-parameter subgroup of the Poincare group has been correctly quantized. You need that all those conserved charges that we derived in the previous lecture, you need to be able to write down operators that obey the right Lie algebra and check that they are all well-defined operators, they all commute with each other in the right way, and only then should you be satisfied that this is a relativistic quantum field theory. So remain skeptical until I've written down all that data. Right, so step one, right? Diagonalization or solution. Diagonalization. So remember how we defined these variables qj prime? It was really easy, wasn't it? You took that matrix O. So we have to wonder, what's the analog of this matrix multiplication in the case of a continuous index? And I'm going to write down a reasonably unique answer. Wherever you see a sum, you have to put an integral. What's the analog of a matrix element? Well, this is just a function of two numbers, right, j and k. So why don't I just put a function of two arguments here, k, x, y. Indeed, that's how you do it. That's the analog of diagonalizing a quantum field, is you've got to find some kernel function k, which is just like a matrix, that has the property that it diagonalizes this Q matrix that comes from this term here. Now, often in textbooks, they make it seem a bit more magical than it is. They will say a statement like, exploiting translation invariance, we know that a Fourier transformation is the way to diagonalize this Hamiltonian. That's true. That's absolutely true. But that doesn't explain the connection with this discrete calculation here very well, does it? I mean, if you're told that you should use the Fourier transform, then you're just asked to accept a statement. What I'd like to do is make it plausible why the Fourier transform is the thing you should go for. So there's one feature of certain symmetric matrices that I want to remind you of that should make you think Fourier transform. So if your matrix is circulant, namely if the entry in the jkth row and column, row j, column k, is just equal to some number, let's call it, loath to use little q, m. If the entry in the jkth entry of q happens to be a function only of the difference of the row and column, the matrix is said to be circulant. I'll draw up a picture of a circulant matrix here. Like 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 7, 7, 7, 7, 3, 3, 3, 3, 0, 0, 0. That's a circulant matrix. The entry in the jkth column is equal to the same entry, and that entry depends only on the difference of j and k. Circulant matrix. If your matrix is circulant, then it's diagonalized by the discrete Fourier transform. I'll use mu. Cool fact, right? If your matrix is circulant, then you build this n by n matrix here, 1 over root n, and in the jkth entry you put mu to the power jk, where mu is not that. Mu is 2 pi I over n. So do that, and every circulant matrix is diagonalized by exactly the same unitary matrix, U in this case. Okay, so this is good and bad. It's good in that they're all diagonalized by exactly the same matrix. It's bad that this matrix isn't actually orthogonal. So you have complex entries and you have to worry about real and imaginary parts. So that's a bit annoying. But it's this fact that I want you to keep in mind. And it's worth doing this calculation, right, just to convince yourself of that statement. Now, you can either do it in Mathematica or something, just check it out. Put in your favorite circulant matrix, just anyone you choose. Choose U to be this matrix, multiply U by Q by U dagger, and be astounded that it comes out diagonal no matter what. Or you could prove it. It's also actually not so hard. It's a really fantastic result. And this is none other than the Fourier transform. I mean, even the name says it, right? Discrete Fourier transform. So it turns out that this Q matrix that turns up in many physical systems, this Q matrix is indeed circulant in exactly this way. And if you have a circulant matrix, you diagonalize it with a discrete Fourier transform. So if you have a continuous circulant matrix, then presumably you diagonalize it with a continuous Fourier transform, otherwise known as a Fourier transform. So I hope that that makes clear the emergence of the Fourier transform in these calculations, because they're the direct analog of this discrete statement here, which I'm going to erase. Discrete Fourier transform has this matrix element. The continuous Fourier transform, kxy, is a function only of the difference, sorry, not the difference, the product of x and y, has exactly this form up above. It depends on your convention. I guess we're going to do ix times y in this course. I think. Yep. Oh no, I've got 2 pi's in there. So the xyth entry, if you like, is e to the ixy. The jkth entry up here is e to the 2 pi. Just forget the 2 pi over n. It's really xy, right? It's the same, exactly the same thing. So by exploiting translation invariance, we know how to diagonalize our Hamiltonian, but actually that wasn't a magical trick. It's observing this fact about circulant matrices. So, but nonetheless, I think it's fair to say that we guess and then check that we can diagonalize our Hamiltonian by making this substitution here. So we make the standard Fourier substitution, and now we encounter this awkward problem with Fourier transforms in quantum field theory and people who like hats. So I like hats for operators, but if you want to take the Fourier transform of something with a hat, then what do? You know, do you do double hat? Do you do tilde hat? Nothing works. Okay, it just looks horrible no matter what you write. I don't know the answer to this conundrum, so you just have to, in this course, know that the argument here tells you that you're in the Fourier space or momentum space. When I use P's and K's, or maybe if I just put like a P, yeah, we can do that. So that subscript P means we're working in momentum space. So we're defining, this is what we know, this is our operator, that we believe it's an operator even though it's not an operator, but we're going to work with this thing as though it's an operator, and we're going to diagonalize our Hamiltonian exactly as we did before for the discrete case by summing over some new variables. These are our analogous to QPs. To Q prime J's. These phi P's. Now, warning. These phi P's are not Hermitian. Work that out. So this is a well-defined expression. The guess here is that this diagonalizes our Klein-Gordon Hamiltonian. And the only way you can be convinced of that is by substituting it into the Klein-Gordon Hamiltonian and seeing that, like magic, it becomes diagonal. Let's call this expression star star. Star star should diagonalize the Klein-Gordon Hamiltonian. And how we're going to do it is exactly analogous to what we did in the discrete case. We're going to construct ladder operators. So a canonical position variable should be a combination of the two ladder operators, A and A dagger. That's all we've done here. And the canonical momentum operator should also be a function of A and A dagger. But of course, remember how we had this one on root 2 omega in the definition of the ladder operators? Well, we're going to take the natural analog here, which is 1 on root 2 omega. But for the momentum operator, the omega appears in a different place. It appears like this. Now I am skipping some steps because the way I'm explaining this as a substitution that you make in your Hamiltonian and then you find that it's diagonal. And that's the way I'm presenting it here. You might be dissatisfied quite rightly. This still looks a bit magical how I've just written down these expressions. You know, I claim that if you write down your discrete versions, in the case of a circulant matrix, you would be writing down something very similar to this. It's a good exercise if you're feeling dissatisfied. If you still don't like that approach, you could just say, well, let phi be some combination of A and A dagger and leave these coefficients to be completely arbitrary. If you really are dissatisfied with what I'm writing here, the magical quality of how these expressions come about, substitute your more general expression into the Hamiltonian, and then ask what do these coefficients have to be in order that my Hamiltonian is diagonal. That's kind of the honest way to do it, but that's a lot more extra derivation steps that we would have to go through, and I'd prefer in this course just to simply to quote to you the answer, the thing that does the job. I don't think we're going to learn so much more from doing the general calculation. But if you're feeling dissatisfied, then do not allow yourself the luxury of writing down e to the IPX, but just the general expression kpx, and then solving for k. You'll get the same answer. But after you see that this works, I think your motivation to do that will be decreased. All right, let's check some commutation relations. We've defined some operators AP implicitly by these expressions here. What commutation relations do these AP operators satisfy? Well, let's find out. We know that phi hat x commuted with pi hat y at equal times is equal to a delta function, don't we? Because that's how we defined it. So it better be the case that when we substitute in these expressions here into a commutator, that we get exactly that answer. So that'll in turn tell us what commutation relations the APs have to satisfy. I've done some of the work for you here. Claim that's what you get when you substitute in star 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 into this commutator here. It's an exercise for you just to check that substitution there, although I think you can probably just sort of see that there's going to be APs and daggers and commutators and stuff. And that has got to equal, of course, delta x minus y. And we can get that exact answer if we choose the commutation relations between these APs and AQ daggers to be none other than, and I'm pretty sure there's some pi's in here, yep, times by the identity operator. I will not use Q, that's a stupid notation. P prime. And now we're like one step away from diagonalizing our Hamiltonian. We've got these expressions for phi and for pi in terms of these APs. These APs obey this very simple canonical commutation relations here. What happens when we substitute this into the Klein-Gordon Hamiltonian? Well, of course, you know the answer. It's going to be diagonal. And indeed it is. And I'll write out, I guess, one intermediate step. And then we'll write out that it's diagonal. That is the answer. It is one step skipped in getting to that answer, but not so many steps. let's just look at these terms, see where they might come from. So I'll just rewrite up the Klein-Gordon Hamiltonian here, which has been lost. Yep. Question? Yeah, what's this? So the question is this a 4 omega p or q or what? So this is 4 omega p, 4 square root omega p prime. I can rewrite that out. Let's just see the origin of these terms here in this substitution. So the d3x comes from the d3x in the Klein-Gordon Hamiltonian. So there's no mystery there. The 4 is coming from this half here, and there's factors of 2 inside the phi. So when you substitute phi into there and pi into there, you're going to get extra factors of 2. That's where the 4s are coming from. We've got combinations like AP dagger, but if you change variables, you see that that's A minus P dagger. So this first term here just comes from the kinetic term. This spatial gradient term here brings down factors of P from these exponents. That's what this minus P dot P bar, P prime is. And then you've got this M squared term here, which appears exactly over here. So there is like one step skipped, if you like, but not much more. And then we're basically ready to write down the answer, because this is just a commutator away from something much simpler, which is why we chose things to be they are. So exercise to go from that line to this line, it's just organizing terms around. And then we use our commutation relation to write out the final answer. All right. The line above is this. So when the dust settles, when you've done all the cancellations and commutators and so on, you should end up with this line here. Now we know what the commutator of AP was. There's a dagger missing. That's what I got wrong. Yep. We know what the commutator of AP with A dagger is, right? It's delta function times by the identity. So that's a big, nasty, infinite number. And there's no way this integral is going to get rid of that infinity. You know, sometimes integrals help you with delta functions. This time, no. So this is some reasonably honest looking operator plus an infinity times by the identity here. Now, observables in quantum mechanics are not actually self-adjoint operators. Measurements in quantum mechanics, you get them by assigning to every yes-no experiment, every experiment with a yes or a no outcome, a Hermitian operator, a bounded operator between 0 and the identity, and you get empirical averages, like the average position, the average momentum, by averaging experiments with yes-no answers with clicks over and over many, many, many trials. So there is no experiment that measures average momentum in one go, right? You get a bunch of clicks, and then you take an empirical average, and then you get the answer. So it's not true to say that this number has an operational meaning in quantum mechanics. In fact, differences in these numbers have operational meanings in quantum mechanics, but this expectation value here by itself doesn't. This is not something we can measure in quantum mechanics, although you may have been led to think that you can. That's what happens when you present the axioms of quantum mechanics in the wrong way. Thus, an observable such as this one here, which has an infinite addition of the identity here, we get thrown a rope because we can never measure this quantity here. There does not exist an apparatus which tells us absolute energy shifts, apart from maybe the gravitational field, but let's put that to the side. We can only measure shifts in the energy differences. That's what you get from spectroscopy. So this here will never appear in any physical calculation, this infinite shift here. So this is physically equivalent, that's what that means, to this operator. And up to that notion of physical equivalence, where you're allowed to add a shift to your observables, we've diagonalized our Klein-Gordon Hamiltonian. We've now obtained its eigenvalues. We know that they are proportional to omega p, and its eigenvectors, which we know, and we'll see in the following lectures, are of the form of the vacuum decorated by creation operators, just like for the normal harmonic oscillator. But that's a subject for the next lecture, and I will stop here. Thank you very much.